Hello everybody. Today we are going to look at applications of integration, and you'll see that we cover multiple applications of integration. So the first application of integration is called the average value of a function, and you can think of it as just like calculating an average basically, where if you had a group of numbers, you would add them up and then you would divide by the total amount of numbers that you actually have. Well, the average value using integration, the average value of a function over a particular interval a to b can be done in a very similar way. So we use integration to actually find the area under the curve, which is like adding all the things up. And then we divide by the length of the interval, which is b minus a. So that's how the average value function works. The formula for the average value of a function over the interval a to b is given by 1 divided by b minus a, all multiplied by the definite integral of f of x dx from a to b. So this is the formula we can use if we're asked to find the average value of a function. So we'll also look at the geometric understanding of that formula as well. Okay, so it says geometrically the average value of a function is the height of a rectangle, and we're calling it y average, AVG for short, where the width of the rectangle is b minus a. So there's our interval a to b. Okay, but it has to have the same area as the area under the curve over the interval a to b. Okay, so think of just finding the area under the curve from a to b, okay, which would be sort of all of this area that I'm shading right now. Okay, all of this, that would be the area under the curve from a to b. And what we're trying to do is find a rectangle that has the same width as the interval, so it goes from a to b, and we're just trying to find the height of that rectangle. What height of that rectangle would give the same area as the area under the curve? So this is the unknown here, the height of the rectangle. And the height of the rectangle is the average value of the function. That's geometrically what this application is doing as well. So let's look at how we can use this. Let's look at some exam questions. So in 2016, this was a tech-free exam question with 3 marks. We were given the function f of x equals 2 sine 2x take away 1. And the function f is defined for minus pi to pi. But the question says calculate the average value of the function f over this interval here. Okay, so not the domain. Ignore the domain. We just need to find the average value between minus pi over 3 and pi over 6. Okay, so the average value, which I'm just going to call AV, average value, equals 1 divided by b minus a. Now that's our interval. So b is pi over 6. Take away the a, which is a minus pi over 3. And that's all multiplied by a definite integral from minus pi over 3 all the way up to pi over 6 of f of x. So 2 sine 2x take away 1 dx. Okay, so that's an expression. That's the expression we would use to calculate the average value. So because it's technology free, we have to work all of this out by hand. We can't go to our calculator to do any of the arithmetic for us. So the constant term before the integration ends up being pi over 6 plus pi over 3 because of the double negative. So just out on the far right hand side, it's pi over 6 plus pi over 3. We can get a common denominator of 6, which is pi over 6 plus 2 pi over 6, which is 3 pi over 6, which is pi over 2, simplified. So this becomes 1 divided by pi over 2, which then becomes 2 over pi once we simplify that. And we can do the integration here straight away. So we're integrating a sine function, 2 sine 2x. Now sine, when you integrate it, becomes minus cos. And we will need to put a 1 over 2 out the front because of this 2x. And there's already a 2 out the front, 2 times a half. Sorry, negative. Let's put a negative there because sine goes to negative cos. And when we integrate minus 1, we get minus x, all between minus pi over 3 and the upper limit is pi over 6. So let's clean this up a bit. The number at the front will be 2 divided by pi. And we'll clean up this antiderivative. So negative 2 times a half, just minus cos 2x, take away x, all between minus pi over 3 and pi over 6. Now I use the fundamental theorem of calculus. I substitute pi over 6 into my antiderivative first. So when we substitute pi over 6, 2 times pi over 6 will simplify to pi over 3. And then we need to calculate negative cos of pi over 3. Now cos of pi over 3 is a half, so it'd be negative a half. Take away the pi over 6, then I substitute pi over 6 for x, that's the upper limit. Then I take away, now I substitute the lower limit in. So we need to substitute minus pi over 3 into our antiderivative, which will be negative cos of negative 2 pi over 3. Now cos of negative 2 pi over 3 will actually be negative a half, multiplied by the negative in front is a half. Take away a minus pi over 3, and I substitute minus pi over 3 in for x. And now I just need to simplify all this. So 2 over pi out the front. And we'll have, if we look here, we have negative a half. And if I expand the brackets here, I have negative a half. So I'll have negative 1. Take away pi over 6. And I have 3 negative signs here. So negative pi over 3 is positive pi over 3. But when I expand the brackets with the negative out the front, it will be a minus pi over 3. So I just need to clean all of this up here. So 2 over pi, all multiplied by minus 1. And now again I need to do some arithmetic. Minus pi over 6 minus pi over 3. Okay, we sort of did that calculation, a similar calculation up here. So a common denominator just out on the side, minus pi over 6 minus 2 pi over 6 is minus 3 pi over 6, which simplifies down to minus pi over 2. So I can write that in my brackets. I can leave the answer like that, but I can actually expand it as well. So that tick, I'm happy with that as being the answer. But if I do expand the brackets, I get 2 over pi times minus 1, which is minus 2 divided by pi. And then 2 over pi times minus pi over 2, well, that'll end up being minus 1. And that is an acceptable answer as well. So the average value of this function here, going back to the problem, the average value of this function f of x for the interval minus pi over 3 to pi over 6 is minus 2 over pi minus 1. So that's the first problem, looking at average value. Problem number 2 is another average value function, but a multiple choice question. So here we have access to CAS to complete this question as well. So here we're asked to find the average value of the function with rule f of x equals log e of x plus 2 over the interval 0 to 3. So we just input all the information into the formula. So the average value equals 1 divided by b minus a. So the b is 3, take away 0, multiplied by the definite integral from 0 to 3 of the function, which is log e of x plus 2 dx. So because we have access to CAS, we literally just input this into our CAS calculator, and hopefully the answer is one of these options. Otherwise we may need to do a little bit of manipulation. So let's have a look. Let's input this into our CAS. So let's create a fraction, and we do 1 over 3 take 0, which is really just 3, all multiplied by a definite integral from 0 to 3, and the function was log e of x plus 2 dx. So that was what we wrote down. Press enter. There is our answer right there. So 5 log e of 5 minus 2 log e of 2 minus 3, all divided by 3. So you'll see that that is option E. 5 log e of 5 minus 2 log e of 2 minus 3 over 3. So I'll just write here, we just use CAS to input this definite integral, as you can see here, and we get the answer pretty quickly. So 74% scored that correct. So moving on to the next question. So another multiple choice. This one here, back in 2012, says the average value of this function here, f of x equals sine squared x, over the interval 0 to a is 0.4. The value of a correct to 3 decimal places is. So here they're asking for average value, but they're telling us the average value is 0.4. So when we write an expression for the average value, it's 1 divided by the interval b minus a. So our interval is a to 0, so it will be 1 divided by a minus 0, because a is the upper limit, 0 is the lower limit, all multiplied by the integral from 0 to a of our function sine squared x dx. So that's an expression for the average value, but we're told the average value is 0.4. So instead of writing the word average value, we replace that with 0.4 because we know that's the average value. and that will equal 1 divided by a, because a minus 0 is just a, all multiplied by the definite integral from 0 to a of sine squared x dx. So this is an equation that we need to solve for the variable a. So again, it's a CAS calculator exercise. We don't want to waste our time trying to integrate and solve this equation by hand when you have access to technology. So we move across over to our CAS calculator and we're going to solve 0.4 equals, so grab a fraction, 1 divided by a, all multiplied by a definite integral from 0 to a, and the function is sine squared x. So the way we type that into the CAS is to go and grab the sine function, just type sine of x, close that bracket, then raise it to the power of 2, like that. Okay, so on CAS, we write it as sine x all squared dx, and then we'll need to do comma a, because we want to solve this equation for a. And it says to 3 decimal places, so I can press enter, or it's better I press control enter for the decimal numbers. Okay, so I get 2 answers here. One's a negative number, one is a positive number. And if we think carefully, the number a, it has to be bigger than 0, because 0 is the lower limit. So the correct answer will be the positive one, positive 1.298. Correct at 3 decimal places, 1.298. Okay, so our answer is 1.298 from CAS, and the answer would be option C. Okay, so you need to be familiar with writing the average value function down, writing the actual definite integral for it. If you have access to technology, use your CAS calculator to do the work. But if not, you can be asked or could be asked to do this as a tech-free question as well, just like this one, just like example number 1. So that's 3 problems on the average value. That was one application of integration. Another type of application of integration is motion in a straight line, also known as kinematics. So we'll go through what this means, what is it. We'll look at some definitions and then look at an example of how this is an example of integration. So motion in a straight line. We use the word particle to represent some sort of body. However, this particle could be large, like a car or a train, or it could be very small, such as a golf ball. And we're looking at the motion of this object, this particle, okay? But only considering straight line motion. So a car traveling on a straight road, okay? Could be a ball hit in a straight line. So some definitions we need to be aware of. One of the definitions is position. The position of a particle moving in a straight line is determined by its distance from a fixed point origin, O, on a line, which we will call origin. It may be given by a positive or negative number according to whether the particle is to the right or the left of O. Okay, so generally if the position of something is -2, we would say that it's 2 units to the left of the origin. And if the particle's position is +5, we would say that the particle is positioned at 5 units to the right of the origin. And obviously, conventionally, the direction to the right of the O of the origin is considered to be positive, just like a number line. So think of it like a number line. Now, some other definitions you need to be aware of. Distance is how far a particle has moved. It is a scalar quantity. Scalar quantity means it's just got size. It's just size. It's the size of something, or the magnitude of something. Displacement, the displacement of a particle is defined as the change in position of a particle. The rule we use for displacement in mathematics is x of t. Okay, so that's important for us to know. Displacement is a function called x of t. Now, there is a difference between distance and displacement. So I've got a visual diagram here just to explain the difference between the two. So here is a particle. Okay, let's assume it starts at the origin, O. Okay, then it moves 5 units to the right to point P, and then it moves 7 units to the left. Okay, 7 units this way, and then stops finally at point Q. Now, what I can say is the displacement of this particle, where is this particle now in terms of the origin? I can say that it's 2 units to the left of the origin. That's the displacement. However, the distance that the particle traveled was a total of 12 units. It went 5 units one way, 7 units another way. So the total distance it traveled was 12 units. So hopefully that's a little example that clarifies the meaning between distance and displacement. Okay. But we need to know that displacement is a function. It's given the function x of t. That will become useful for us later on. Velocity, we need to know what velocity is. So velocity is the rate of change of position with respect to time. So it's a derivative, basically. It's a rate of change. And we'll look at the formula in a minute for that. You could be asked to find an average velocity, which would just be like finding the average rate of change. Okay, so the average velocity, so assuming a particle moves from x1 at time t1 and it moves somewhere else, so it moves to x2 at a different time, so t2, then your average velocity is just a gradient. x2 take x1 divided by t2 take t1. Okay, it's the change in position divided by the change in time. Now, some interesting facts about velocity. If the velocity is positive, so if it's a positive number, the particle is assumed that it's moving to the right. If the velocity is negative, or a negative number, the particle is assumed to be moving to the left. And if the velocity of a particle is 0, then we say that the particle is instantaneously at rest. So it's not moving. So it's quickly stopped. Okay, so they're very important interpretations of the numbers that we will need to know. So here is the definition here. So velocity can be determined by the rate of change of position with respect to time. So that's velocity v equals dx dt. This is a function that we're going to be using. Now we can also use some different notation rather than just dx dt. We could actually say that velocity is x dot with a dot on the top. The dot just means the first derivative. Or I could use the notation x of t with a dot on the top, meaning it's the first derivative of position. So there are some alternate notations there, but the one we generally use in math methods is just v equals dx dt. Okay, so that's generally the one that we would use. You could be asked to calculate the speed of an object. So the speed of an object is the magnitude of velocity, meaning it's the absolute value of velocity. So here velocity could be a positive, a negative, or 0. So say for instance the velocity of a particle is negative 2 meters per second, then the speed would be 2 meters per second, positive. We take the positive version of that, the absolute value. Okay. There's also a formula for the average speed as well, if you're asked to ever calculate that, which is just the distance that it traveled divided by the time interval. So just some useful formulas that may or may not um, help you in some questions there. If you're interested, we don't do a lot of work on this in math methods at all, mainly for physics students and specialist math students, but um, velocity and speed, the most common units of measurement are either meters per second, centimeters per second, or kilometers an hour. And there is a little conversion table like here that shows you how you can convert between the three sets of units if you need to. So you may need to refer to that, but most likely you won't. And the last definition we need to know is acceleration. So acceleration is the rate of change of velocity of a particle. So that means it's dv dt. The rate of change is a derivative. We could be asked for average acceleration over a particular time interval. So that would just be v2 take v1 divided by t2 take t1. Some important facts about acceleration. They can come in handy. If the acceleration of a particle is 0, then the particle it's still moving, but it's moving at a constant velocity. If a particle's acceleration has the same sign as its velocity, so meaning acceleration is positive and velocity is positive, the particle is speeding up. If a particle's acceleration has the opposite sign to its velocity, then the particle is slowing down. Okay. And so here is our formula for acceleration. Okay, so I'm putting a star next to the formulas that you're going to be using, the takeaways that you really need to know. So acceleration is the average rate of change of velocity. So it's a equals dv dt. But recognizing that dv dt, that velocity was the first derivative of position, acceleration would then be the second derivative of position. So we have two expressions for acceleration. Acceleration could be dv dt or the second derivative of position. The symbol we use is d squared x divided by dt squared. And we could use the dot notation and we would put two dots because it's the second derivative. So acceleration equals x of t with two dots on the top, meaning the second derivative of position. Okay, and the most commonly used units for acceleration are centimeters per second squared or meters per second squared. Now for us, because acceleration involves a derivative and velocity back here involves a derivative, okay, we can actually move between the three functions, position, velocity, acceleration, using derivatives or antiderivatives, so integration, depending on which way we need to go. So I could, using integration, I could say that the position function, x of t, could be calculated by doing the antiderivative of the velocity function with respect to time, and that the velocity function can be calculated by finding the antiderivative of the acceleration function with respect to time. Okay. So here's a little diagram that shows you when you'll need to differentiate and anti-differentiate when you move between the three new functions: displacement, okay, which is x, velocity, which is v, and acceleration, which is a. So if you need to go from displacement to velocity, follow the pink arrow here, which means you should differentiate. If you need to go from velocity to acceleration, follow the pink arrow, so differentiate. However, if you need to go backwards, say for example, you have the acceleration function and you would like to find the velocity function, you need to anti-differentiate, follow that blue line along here. Okay, and if you've got the velocity function and you would like displacement, position, you find the antiderivative of velocity, and that will go back to your function displacement. Okay, so here you can see why it's an application of integration. We could be doing derivatives or antiderivatives. Okay, but this is really an important takeaway from the exercise. Okay, so displacement is x, velocity is v, acceleration is a, and this diagram shows how you can move between the three functions, whether it's finding derivatives or antiderivatives. So this is what we're going to be using here. So we've got an example. A person standing on a springboard 10 meters above the surface of a pool throws a ball vertically up in the air. The ball is thrown using their arm at a height of 1.5 meters above the springboard and has an initial velocity of 15 meters per second. Assume the ball falls towards the pool with an acceleration of -10 meters per second squared. So 3 questions. Find the time at which the ball reaches its maximum height. Hence, find the maximum height of the ball above the pool surface. And then finally, find the time in seconds correct to 1 decimal place that it takes the ball to reach the pool surface. So we've got a diagram on the side here that explains this situation here. So here we've got a person on the springboard. Okay, they're 10 meters above the pool surface. They throw this ball up. It reaches some sort of maximum height, and then it will come back down and land in the pool. And you can see that the height of the person's arm is 1.5 meters above the springboard. Okay, so the first question is find the time at which the ball reaches its maximum height. The time. So how long? When we throw this ball up, how many seconds is it going to take to reach its maximum height? Okay, now you actually need to understand a little bit of physics for this problem. So one of the very important things about velocity is this. I'm going to put a little box around this one. That's really important. Okay. If the velocity is 0, then the particle is instantaneously at rest, meaning it's not moving. Okay, the particle is not moving when the velocity is 0. So you think about this. Throw a ball up in the air. It needs to stop very quickly, so instantaneously, for it to come back down. Otherwise, it would just keep going up. So when the ball reaches its maximum height, the velocity is going to be 0. So right at the top of this problem, when the ball reaches its maximum height, the velocity is 0 because it's instantaneously at rest. It stops and then falls. And that's a really important piece of information you need to know. And it's not actually written into the problem. It's actually something you need to know about velocity. Okay, so very, very important here. Now, so really I want to know when the velocity is 0, the time it takes for the velocity to be 0, which is max height. Okay, but if I go back and read all this again, it says the ball falls towards the pool with an acceleration of -10 meters per second. Okay, so what I know from this problem for part A, I know acceleration is -10. That's just a number, -10 meters per second squared. Okay. Can I find the velocity from acceleration? Is it possible? So let's go back to this diagram here. If I've got acceleration, how do I move to velocity? So it says to anti-differentiate. Okay, so let's anti-differentiate. So I want to find velocity. So v equals the antiderivative of acceleration, which is minus 10 dt with respect to time. So finding the antiderivative minus 10 is just minus 10t plus c. Okay, so there's my velocity function. Velocity equals negative 10t plus c. Now the plus c, do I have some information that can calculate the plus c? I do, because this is all about velocity. Reading the question again, it says, the ball was thrown with an initial velocity of 15 meters per second. So that actually means v equals 15 when t equals 0, right at the beginning. Initially means when t equals 0. So that's my initial conditions here that I can use to find the plus c. Okay, so v equals 15 when t equals 0. Substitute those numbers in, which would give me 15 equals negative 10 times 0, so that will give me 0. So c is 15. Therefore, my velocity function is negative 10t plus 15. Okay, that's my velocity function. I haven't actually answered the question yet. The question says, find the time when the ball reaches maximum height. Now, here, when the ball reaches maximum height, the velocity has to be 0. So now I come back here. Okay, so max height means v equals 0. That's the meaning of this problem. The maximum height happens when the velocity is 0. So here I just put v equals 0. So 0 equals minus 10t plus 15. And I solve this for t. So I subtract 15. And then I'll need to divide by a negative 10. So it would be t equals minus 15 divided by minus 10, which is divide both numbers by 5, which is 3 over 2. Okay, s for seconds. So what this is saying is it takes 3 over 2 seconds, which is 1.5 seconds. If you want to write it as a decimal number, you can. So it takes 1.5 seconds for the ball to reach maximum height. So I'll just write that in there. So it takes 1.5 seconds to reach max height. Okay, that's our answer to part A. Find the time it takes to reach maximum height. So 1.5 seconds. Okay, that's how we do problem A. So we started with an acceleration. We found the velocity by doing the integral, the antiderivative of acceleration. Part B. Hence, find the maximum height of the ball above the pool surface. So how high, what's the highest the ball reaches above the pool surface? Okay, so we need to think about this problem here and say, okay, well, out of the 3 new functions that we've got, so out of displacement, velocity, and acceleration, which one of those would allow us to find a height? So definitely not acceleration, not a velocity. That just tells you like how quick something's moving. But displacement is a distance. How far away are you from somewhere? So we actually want the displacement function. So we have the velocity. We need to go to displacement. So this tells us to anti-differentiate. So that's what we need to do for part B. We need to do another antiderivative. So part B, we want to find the x function, displacement. Now that's going to equal the antiderivative of velocity, which is minus 10t plus 15 dt. Okay, so we do the antiderivative. the minus antiderivative of minus 10t will be minus 5t squared. The antiderivative of plus 15 will be plus 15t. Okay, plus another constant of integration, so plus c. So, again, there has to be some information in the problem that will enable me to work out this plus c. Okay. So, remember also too that we're looking at the distance the ball is above the pool surface. Okay, so if I go back to the diagram, right before this person throws the ball, which means when time equals 0, right at the beginning, what's the height the ball is above the pool surface? Okay, so I'm putting a little red dot there. There's the ball right at the start. So how high above the pool surface is that now? So it's 1.5 plus 10. So the total distance that the ball is above the pool surface in the beginning is 11.5 meters. So that's our initial condition. Our initial condition is x equals 11.5 meters when the time equals 0, right in the beginning. Okay, that's our initial condition. So we can use that to find the value of c. So you'll need to substitute those numbers in. So substituting the number t for 0, so that will actually be c will equal 11.5 meters. Okay, so therefore c will equal 11.5. If you wanted to write it as a fraction, you can. We could say it's 23 over 2. 23 over 2, if we wanted a fraction, as opposed to the decimal. So therefore, my displacement function, x, equals minus 5t squared plus 15t plus 23 over 2, if I want to use the exact, use fractions. Okay, so that's my position. So now I need to find the maximum height. Okay, what's the maximum height that the ball reaches above the pool surface? Now, from part A, I actually know that it takes 1.5 seconds to reach maximum height. So I can use that number to help me find the maximum height. I can substitute t equals 1.5 into this. So max height occurs when t equals 1.5, because that's what we worked out in part A. So I substitute t equals 1.5 into this equation here. Okay, so x equals minus 5 times 1.5 squared plus 15 times 1.5 plus 23 over 2. And I'm just going to use my CAS to work this out. So negative 5 times 1.5 squared plus 15 times 1.5 plus 23 over 2. As an exact number, I get 91 over 4. If I want a decimal number, it's 22.75. Okay, just to give you a bit of a realistic understanding of what that means. So 91 over 4 is the correct answer. 91 over 4 meters. But as a decimal number, that's just 22.75 meters. 22.75 meters. So that's the maximum height that the ball reaches above the pool surface. 22.75 meters. Okay. Now for the last part, part C. Find the time in seconds, correct to one decimal place, that it takes the ball to reach the pool surface. Okay. So we need to think logically about this one. We want to know the time in seconds it will take the ball to reach the pool's surface. Okay, so let's look at what we've calculated already. We already know it takes 1.5 seconds to reach maximum height. Okay, so when we throw the ball up, I'll use a blue marker here. So throw the ball up to reach maximum height, that's 1.5 seconds. So I'll put a little arrow that's going up. To come back down to where the ball was thrown from, that also takes 1.5 seconds as well. Same time up and down. Okay. Then we could then just figure out, all right, how long will it take to go from here back down to the pool surface? So this time right here with a question mark is what we need to find. Okay, so we've already got 3 seconds, 1.5 seconds up from the person's hand, then 1.5 seconds back to where their hand would be. So that's a total of 3 seconds. Then we just need the time it's going to take to go from the person's hand down to the pool surface. Okay, which we know. We actually know the distance that is, don't we? We know that's 11.5 meters. Okay, however, that's actually negative 11.5 meters. Okay, because think of that red dot. Think of that red dot as the origin, O. Okay, and the height above the pool surface, meaning going upwards, up to the ball, that's a positive number. When we go back down, when the ball goes back down, that's a negative number, according to the origin. Okay, so the origin is actually the pool surface, not where the hand is. The origin is down here. Okay, but we know the problem, we know the distance that the particle needs to travel is 11.5 meters, but negative 11.5 meters, going in the other direction. So, for part C, we've got our displacement function. I want to know when x equals negative 11.5 meters. Okay, and that'll give us the time. That will give us this time, and then we can add the 3 seconds on to the answer. So I want to solve, when does negative 5t squared plus 15t plus 11.5, when does that equal negative 11.5? So if I add 11.5 to both sides, I got negative 5t squared plus 15t 11.5 plus 11.5 is 23, so that would be plus 23. When does that equal 0? Okay, so I can solve this quadratic on my calculator. So solve negative 5x squared plus 15x plus 23 equals 0, comma x. We'll get some decimal numbers there. So we've got two answers. But we reject the negative because there's no such thing as negative time. Remember that this variable x stands for time, t for time. So we reject the negative and we get 4.117. Correct the 3 decimals here. So let's say t equals 4.117 seconds. So we can now answer the question, which is find the time it takes in seconds that for the ball to reach the pool surface. Okay. So we've got 1.5 plus 1.5 plus the 4.117. So total time t equals 1.5 plus 1.5 plus 4.117. And then we add those numbers and then just round to 1 decimal place, which is what the question is asking there. So 1.5 plus 1.5 plus 4.117. So to correct the 1 decimal place is 7.1 seconds. 7.1 seconds in total. Okay, so this, as you can see, this problem is an application of integration. So we're learning three new functions here: displacement x, velocity v, acceleration a. They're linked together by either using differentiation or anti-differentiation, according to this little diagram here. So you'll find this very useful when answering problems on motion in a straight line. So that's the second application of integration. And the last thing that you need to be able to do is rates of change. So we did rates of change in differentiation. So it's really just a look back at some of that. So it's just straight into an example here. So last example, the rate of flow of water from a reservoir is given by dv dt equals 1000 minus 30 t squared plus 2t cubed for the interval t is between 0 and 15 inclusive. V is measured in millions of litres and t is the number of hours after the sluice gates are opened. Find the rate of flow in millions of litres per hour when t is 0 and t is 2. So it says find the rate of flow. Okay, well, the equation we're given is the rate of flow. So you just substitute 0 in and t equals 2. Okay, so for part A, when t is 0, we get dv dt equals 1000. And when t equals 2, you just have to substitute the number 2 into the function, which gives us 896 if you do that substitution. Okay, If you substitute t equals 2 into here, you can do that on your CAS calculator to double check. For part B, find the times when the rate of flow is a maximum. So I want to know when the rate of flow here is a maximum. And what is the maximum rate of flow? Okay. So there's a number of ways you could do this. You could just do this on the graphs page. You could sketch this function, which is the rate of flow, and then find the maximum rate of flow. Okay. You could use calculus as well. Okay, so finding the maximum of something, you find the derivative and you make that equal to 0. So either approach would be okay. So here we could solve derivative equals 0. Now you would have to find the derivative, even though you've been given a derivative. So you've got to be really careful in this problem. So this is the rate of flow. You want the maximum value of this. So you find the derivative and then make it equal to 0. Okay, so solve derivative equals 0. We could do that fairly quickly. The derivative, when you differentiate 1000, that'll go to 0. Minus 30t squared will be minus 60t. So it would be minus 60t. And there's a cubic function. So the derivative of 2t cubed would be 6t squared. So plus 6t squared. And that equals to 0. You can factorize this quite easily by taking a 6t out as a common factor, which would be 6t bracket minus 10 plus t. Use the null factor law. So it would be t equals 0 or t equals 10. Okay, so find the times when the rate of flow is a maximum. So it's t0 or t equals 10. You'd have to double check because these might not be maximum values. Remember, these are stationary points. That's saying there's two stationary points, but the stationary point could be a minimum. So you could use a sign diagram to prove which one is the maximum, or you could just sketch the function on your calculator. Okay. So I'm going to go for a sketch now. Let's go and... So you could take the algebraic approach like I just have, or we could sketch the function 1000 minus 30x squared plus 2x cubed. Okay. Now I'm going to put a domain restriction because I only want to draw it between 0 and 15. The function is only valid between 0 and 15. So it would be ideal to put that domain restriction in. So here I'm going to need to change the zoom because I can't see it. So I'm going to go menu for zoom fit. Okay. Zoom fit tries to give you a domain. Now it hasn't gone all the way out to 15, so I can just push the graph until I need it. So this now says 15.02. Okay, so it's somewhere, the max is there. The end of the graph is there. Okay, so this is what the function looks like. Okay, so you can see the two t values I got here, 0 and 10, they're stationary points. So 0 is up here, so this is a maximum, but the t equals 10 is a minimum. Okay, so we can ignore the t equals 10. That's not a maximum when the flow is a maximum. So here, it could happen at 0. So let's substitute 0 into the function. So menu, trace, graph trace, we put 0. The calculator tells us it's at 1000. So the rate of flow is 1000 up here at the maximum value, but you should also check endpoints as well because the function is valid to 15. Now, when t equals 15, if the y value is higher than 1000, then that's where the maximum rate of flow would be. So let's just trace the graph again and substitute 15 in, and you'll see that when t is 15, the rate of flow is 1,000. So the highest rate of flow possible, the maximum rate of flow, is 1,000. It happens 2 times, at t equals 0 and t equals 15. So I come back in here, okay, and I can just say max flow equals 1,000. Okay, and that occurs when t equals 0 and when t equals 15. Okay, it's at its highest at either one of those values of t. Okay, so remember, always check endpoints because of the absolute maximum or minimum. But the max flow is 1,000 and it occurs at t equals 0 and at the endpoint as well when t equals 15. So the max flow is 1,000 and the times, the question is asking for the times. So the times are when t equals 0 and when t equals 15. So that takes care of part B. Sketch the graph. So we've already done that. We've done that on CAS. Okay, so you would need to construct the graph which starts up here and it's a max and it comes down, it has a minimum, comes up and then stops there. So it stops at 15. Let's stop drawing it at 15. This is 1,000 up here and the endpoint right there is 15, 1,000. And this turning point here happens at 10 down there. So this is the sketch you would need to draw out yourself. So this is the sketch you need to produce. Then in part D, you're asked to find the area under the curve between t is 0 and t is 10. So we can see where that would be in this diagram here. So again, we just use our CAS to figure that out. But area equals, let's write a definite integral though, just to show the mathematics. So it's a definite integral between 0 and 10 of the actual function, which is 1,000 take away 30t squared plus 2t cubed. So this, by writing this down with respect to time, it shows an examiner that you understand how to mathematically calculate that area by writing the definite integral. But now we can just use our CAS to do that. Okay. I will do it on the graphs page and hope that the answer is, you know, not the square root of something. Otherwise, I will have to go and do it on the calculator page. I could do it on the calculator page as well, but since I've got the graph here, I'll go menu, analyze the graph, integral. The lower bound, just type 0 and press enter. And then it asks for upper bound, so type 10 on the screen and press enter. And so it shades the correct area, and great, it's a whole number, 5,000. Okay, so the area is 5,000. So I come back here, the area is 5,000, even, okay. And then I finish the question off. Which is part D, part 2. What does this area represent? Okay. So I've got to think about what would the area under this curve represent when it's talking about the rate of flow. The rate of flow. Okay, the equation that we're actually looking at here on the screen, it's the rate of flow. So the area under the curve in this case would actually mean that 5,000 million liters of water has flowed from the reservoir in the first 10 hours. Okay, so because between 0 and 10 is 10 hours, so 5,000 million litres of water have flowed from the reservoir in the first 10 hours. That's the meaning of this area. So 5,000 million litres of water has flowed from the reservoir in the first 10 hours. Okay, so that's how I would finish off that problem there, because it says the amount of water is in millions of litres. Okay, so our area was 5,000, so it's 5,000 million litres of water has flowed because it's about the rate of flow from the reservoir in the first 10 hours. So this is an example of a rates of change problem. Okay, so yes, it does involve some of the classic skills you've already learned before, which is finding a derivative and making it equal to 0 to find a minimum or maximum, but also interpreting the numbers, checking them to see which ones are relevant, which ones are the maximums in this case. Check endpoints, okay, for absolute maxima and minima. So we needed to check the endpoint of t equals 15, because that is also when the max flow occurred as well there as well. Sketching graphs, yes, we can do that on CAS, and then finding areas as well. So now there's the integration part. Okay, so this is the exercise applications of integration. So we've got three main ideas in this problem. We had the average value function at the start. We had motion in a straight line, so that's looking at displacement, velocity, and acceleration, and then rates of change.